Welcome to the first semester calculus stream. I just had the idea of doing this for my class, then realized why not just make it for anyone else who is in calculus and wants to review before finals, because it's final season right now. Alright, so anyway, as you can see on the screen here, we have some topics. Here's the approximate times. I'm probably going to deviate from that a little bit. I'll try to go a little bit quicker than that just so that we can get through everything before like 9 p.m. today. Because this is video 1, and so this is video 1 out of 3. So gonna go over limits and continuity. One of the applications of limits is Riemann Sums, so I'm gonna go over that here, and then evaluating derivatives. That's kind of another limit related thing, so that's all gonna be in this video. The next one's gonna be all derivative related stuff and some integrals. And then the last one's going to be integration and differential equations. So this is for Calc AB and BC, not just AB, not just BC. So it'll have topics for pretty much everything. Alright, without further ado then, let's get started. Okay, first thing that we need to understand in calculus is what is a limit. The general idea of it is just you have the prediction of the behavior of a function given a condition. So this thing down here, you've seen this if you're in calculus. The limit as x approaches a of f of x equals L. L is that prediction. So you're going to get some sort of a value given a function, or a value depending on the function and the condition. The condition here is x approaches a. So you can also have a few other variations where x approaches a and you have an exponent looking thing as plus or minus. Plus would just mean that you are looking at what's happening on the right of the function, and then minus is just what's happening on the left of the function. How does left of, not the function, of the value a. Sorry. But yeah, so different functions can do different things. Like for instance, if you have something that goes like this, then on the left is approaching a specific value, on the right is approaching a different value. Okay, and then if we look over here, this is the same kind of idea except looking at the infinities. So as x approaches positive infinity or negative infinity, this basically just is, what's it called, horizontal asymptote. So what happens to the function at the infinities, plus or minus infinity? So essentially, if you let x get really big, either on the left or the right, what happens to the function? Where does it stabilize? Okay, so with limits, there are some strategies we can use in order to evaluate them. Essentially, algebra, or L'Hopital's rule. For algebraic manipulations, there are things such as factoring, conjugates, trig identities, etc. L'Hopital's rule, we're going to talk about it here, even though we haven't gone over derivatives just yet in the stream. But I figured since we're doing evaluating stuff here, we might as well just go over it anyway. So I'm going to do both the examples here with just algebra stuff, and then apply L'Hopital's rule to it as well, so that we can see how that works. Alright, so first thing that you always want to do with a limit is just try what's called direct substitution. And what is that? That is literally directly substituting this thing into x. So if we do that, then we get the square root of 0 plus 16 minus 4 divided by 0. Okay, you can pretty easily see that this becomes 4. 4 minus 4 is 0 divided by 0. Okay, indeterminate form. So let's do something to this. Let's manipulate it. Before I continue, notice that over here I do not have limit written there, versus over here I do. The reason for that is because over here, I've already used the limit. I've already directly substituted in. Over here, I haven't yet. I'm just doing stuff to make it so that this works. So I'm manipulating it. So limit still has not actually happened yet. Just gonna do stuff to it first, and then we're gonna make the limit happen. Substitute that thing in. Alright, let's go. Here is one where you'd want to use the conjugate. The reason for that is conjugate, if you multiply by it to here, you're going to get the first thing squared minus the second thing squared. The purpose for that is to get rid of the square root. So chances are, if you have a square root, you're probably going to want to do that. So let's do that. And then we will end up with this. And don't forget to make this the denominator. Don't make the common mistake of making it just x or just this thing. I see that quite a bit, so don't make that mistake. Okay, so once you do this, you can see that those two will subtract out. Then we get the limit as x approaches 0 of x divided by x times that hot mess. And then the x's can divide out. And then we end up with 1 divided by this thing left. Whoops, that's supposed to be a plus. And then we end up with 1 over square root of 16 plus 4, 1 over 8. Alright, so let's review kind of what happened here. Essentially, I applied the conjugate. Things were able to subtract out. Then the x was able to divide out. Then we were able to do direct substitution and get a number. So, indeterminate. That's what this thing is, right? Let's actually try this again. So if you're watching this on the stream, obviously you can't pause the video here. Just take a quick picture as I say this. But if you're watching the video part of this uploaded onto YouTube, you can pause before I erase this. So I'm going to erase this right now, then we're going to do L'Hopital's rule on it. Alright, so as I'm erasing this, let's just talk about it. So L'Hopital's rule, essentially if you get an indeterminate form through direct substitution, then you're able to apply L'Hopital's rule, which is taking the derivative of the numerator and taking the derivative of the denominator, then taking the limit of that result. And when you do the L'Hopital's rule step, you want to put LH on top of an equal sign or something like that. Make it clear that you're doing that so that the reader's not looking at you like, what are you doing? Okay, so if we take the derivative of the numerator, the 4 is going to be 0 because you take the derivative of number, nothing. And then here, you're going to get 1/2 times x plus the quantity x plus 16 to the negative 1/2 power. That's just 1. Okay, let's just do this out then. So that's the same thing as having this. Substitute in 0, you get 1 over 2 times the square root of 16, which is 1 over 2 times 4, which gives you 1 over 8. Same thing that we got in the previous one, right? Okay, so yeah, just as long as you get an indeterminate form, you can do that, unless, of course, the problem is asking to do it a certain way. Then obviously, if the problem is asking that, do it the other way, don't use L'Hopital's rule. Alright, so let's move on to another one and see what we can do here. Alright, so if we substitute in directly right now, we'll see that we get 2 squared, which is 4, plus 2, minus 6, all divided by 2 minus 2. That's going to be 0 over 0. Again, we can do stuff to it. So let's try applying factoring, because this thing looks like it could be factored, right? So that'll be x minus 2 times x plus 3 divided by x minus 2. X minus 2's can divide out. You get the limit as x approaches 2 of x plus 3. You can substitute in the 2, then you get 2 plus 3, which is 5. Alright, so let's see what will happen if we use L'Hopital's rule on this. So I'm just going to do that down here. So technically you would just go from the 0 over 0 part to here. Limit as x approaches 2 of, let's take the derivative of the numerator, which is 2x plus 1, and then the denominator derivative is just 1. If we substitute in 2, we get 2 times 2 plus 1, which is 5. So they both match. That is what we're looking for, and we're good. Okay. So now let's see what happens next. We're going to do continuity. So let's just briefly talk about what is happening here. For continuity, essentially the idea behind it is when you draw a graph, you don't have to pick up your pencil or pen or whatever you're writing with. So the general definition given in textbooks in high school is this thing. The function f of x is continuous at x equals a if these three conditions are met. F of a is defined, the limit as x approaches a of f of x exists, and the limit as x approaches a of f of x equals f of a. So essentially, if you just check for this one, then you're good, because you're implicitly going to check for the other two as you do that. So that's just like a quick thing that you can think of. You can just literally think it equals, it's just that. Alright, so if we had a function like, let's say, f of x equals, I don't know, let's just say something that's like obviously x squared plus 1 over x plus 2. So this is an abbreviation I use, CTS. I'm just using that now because it's quicker. And stream. So, okay, continuous at x equals 1. Okay, let's check that. F of 1 equals 1 plus 1 over 1 plus 2, which is 2/3. Okay. Limit as x approaches 1 of f of x equals, we can directly substitute and we get 2/3, which equals f of 1. So yes, this is continuous. What about at x equals -2? Well, f of -2 is undefined because you get something over 0, right? That's pretty clear. As if you're taking calculus, you should probably be able to see that pretty easily. Since you see -2 plus 2 in the denominator. So we technically don't even need to check after this because we know it's undefined by this point. Alright, anyway, let's move on to an application of continuity, which is called the intermediate value theorem. Here's the theorem. Let x be continuous on the interval from a to b and consider some number y sub 0 between f of a and f of b. Then there is some x equals c on a b from a to b such that y sub 0 equals f of c. Okay, so what that basically means is... should have put some more space. Oh well, let's just use this part. Let's see, we got a function. Here's a. Here's b. So here's f of a. Here's f of b. This is continuous, right? You have to pass through everything in the middle. Everything between f of a and f of b. Everything in between there has to be hit if the function is continuous. Therefore, if you are looking for some value such that, let's just say, so y0 is somewhere in between this red, right? That means there is going to be some x value that's going to make this thing be a y value that happens here. So it's pretty intuitive if you kind of think about it that way, rather than look at the theorem itself and go like, oh my gosh, symbols and words. So let's use that idea over here on this problem. so I got a table. It has velocity and time. Let's just say that v of t is a differentiable function. Then that tells us one thing about it. Well, a few things. First, it's differentiable, and second, it actually tells us that it is continuous, because differentiability implies continuity, right? Versus continuity doesn't necessarily imply differentiability. Alright, anyway, so we know that this is continuous, and a question asks, how many times does v of t equal 21 on the interval from 5 to 9? The interval from 5 to 9 is here, right? And the question is, how many times does it equal 21? We can't necessarily say, but we can say at least twice. Because f of 5 and f of 7 are 20 and 25. Or v, sorry, not f. So because 21 is in between these two, then we know at least one time v of t equals 21 there. And then also here, same idea. At least one time v of t is going to equal 21 between these two because of the fact that this is a continuous function. So you can say at least twice. If you're watching this, you're probably either from my AP class or another AP class, because those are the only people that know about this, I think. So, quick thing about this, you might see things like this on AP, like they'll say things like this, and that's basically intermediate value theorem in disguise. There's also mean value theorem in disguise. That happens as well. That'll happen later on in a different stream. Okay, so let's apply this whole continuity and limits thing to Riemann sums. So, how do we get the area between this right here? So, what you can kind of do is you can either get a bunch of rectangles like this, and then find the area of those rectangles. Or you can do something similar as well, but with, I should use a different color, but with trapezoids, which you can kind of see is a little bit closer, but still an approximation. So let's think about what this really means. Rectangles. For rectangles, you need, in order to find the area, you need the base and the height, right? And you're essentially adding a bunch of bases and heights multiplied together. So, as you can see what I have written, I have this summation notation. This means you add this. You're adding this thing here. So we're going to add base times height a lot. Why did I write triangle method? That's supposed to be trapezoid. Okay, so I'm going to write trapezoid. Sorry about that. Well, I just made all these notes right now because I decided to do this morning, but yeah. Anyway, so trapezoid. The formula for the area of a trapezoid is base 1 plus 1/2 times the quantity base 1 plus base 2, all times the height. Okay, so real quick, basically if we're going to find, let's just say this trapezoid. I'll do it in red. The area of this trapezoid. Base 1 and base 2, remember, those are the sides of the parallel, the lengths of the parallel sides. And height just means the length in between them. So it doesn't necessarily mean that height is something going up and down. And base doesn't necessarily mean something going left and right. So just keep that in mind as we do these things. So let's just kind of do that here and see what we get in terms of formulas. So here's this word, parametrize. We want to parametrize the height. So, well, also the base. In this case, let's look at what our base and height are. So let's just say we're going to use a certain number of rectangles. Let's just say 2, for instance. And let's just say we're using left rectangles for now. How big is this? Each of these little areas, that's going to be the base, right? Well, if we took the distance between A and B and divided by 2, we would get what we want, right? What if we had 3 rectangles? Then we do the same thing, but divide by 3 instead. So what if we want to generalize that and say like just n number of rectangles, any of them? Then it'd just be b minus a, which means the distance between b and a divided by n. So we know we're going to have a delta x somewhere. I'm going to write it at the end because that's just where we tend to write things. You'll see why later on. If you're familiar with integrals, then you can kind of see where this is going already. Because that's basically dx. If you didn't notice that before, then, well, that's dx. Alright, so let's look at this. What is the height? If we have, let's just use 2 rectangles for simplicity's sake. How do we find this? What is that value? Well, that's actually f of a. And this is f of a plus delta x. Because to get from a to there, you just add delta x. A distance of delta x from a. So here we have a plus delta x. If we had, let's just say 3 of them, that could definitely look better, but oh well. Then we have f of a plus delta x, f of a plus 2 delta x. So what do we notice here? Well, we notice this is basically going to be f of a plus 0 times delta x. This is f of a plus 1 times delta x. Here's f of a plus 2 times delta x. But we have 3 rectangles, right? So the interesting thing about left then is we can start at a and then add something times delta x. In this case, I'm going to have us add k minus 1 times delta x. Because in the end, we're going to get k minus 1 of them, or n minus 1 of them, right? That's what we saw up here. So what about other ones? Let's do the same thing here. It's just with the right ones. So here, we don't start at f of a. We start at f of a plus delta x. Then we go to f of a plus 2 delta x. And then we end at f of a plus 3 delta x. Okay, so we can already notice the difference, right? We use 1 delta x over. So for right rectangles, we can actually write this as f of a plus k delta x, and then that'll work perfectly. Midpoint is bizarre. Okay, not that weird, but essentially, let's look at what that would be then, using just 2 actually, because it'll be easier. So if we're looking at the midpoint, I'm going to use red on this. So just a different color so that we can see that a little bit better. Alright, so what is this? We get f of what? And then f of what? So here, how do we get that x value? That's going to be a plus a delta x over 2, right? Okay, well, wait. Yeah, a plus, so here's a, this is a plus delta x, right? So a plus delta x, all divided by 2. So we got something bizarre there. So we can write that as 2a plus delta x all divided by 2, or a plus delta x over 2. Alright, well, how about here? Here we have, this point is a plus delta x, so I'm going to do the work over here. F of a plus delta x plus a plus 2 delta x. So, f of a plus delta x plus a plus 2 delta x all divided by 2. So this is 2a plus 3 delta x all divided by 2. In other words, a plus 3 over 2 delta x. Alright, so how do we get this? We see that we have 1 over 2 delta x, a plus 1 over 2 delta x, and an a plus 3 over 2 delta x. So it ends on this. So let's see, what can we do? If we let this start at k equals 1, then it'll be a plus, we're going to have something over 2 times delta x. And then that delta x outside. Let's see, what can we do with that? So if we want this to equal 1 at first, and we want them to be all odd, so how do we make things odd? We make them even, then we can add or subtract 1 from them, right? Because between any even number, there is an odd number. So let's make it even by multiplying by 2, and then we want this to equal 1 when k equals 1, so 2 times 1 is 1. We need to subtract 1 from it to get the other thing. So we can do that for midpoints. So this is how we can parametrize the heights and the everything. So parametrize is just a fancy word to mean write in variables. Okay, trapezoids. So there's actually a pattern here. Because if we look at, so first of all, delta x is still b minus a over n, same idea, right? So if we look at things like this, we have a, we have b, a plus delta x, a plus 3 delta x, 2 delta x, a plus 3 delta x, a plus 4 delta x. So what we end up with is 1/2 f of a plus f of a plus delta x times delta x. And then you will add another 1/2 f of a plus delta x plus f of a plus 2 delta x times delta x. So this is added twice. This is actually going to be added twice, and so will this. So you'll get 1/2 of f of a plus f of b plus 2 times f of all the ones in between until that point. So how can we write that as a formula? F of a plus, and then something times delta x, right? So that'll be, let's see, if k starts at 1 and ends at n, let's look here. This is n minus 1, right? Because in here, n is 4. So we can just say k minus 1 times delta x. So if you kind of memorize this, understand it, or do what I did here, and I literally just derived it. I didn't quite know if I was going to get it correctly when I wrote it, but I'm like, okay, yeah, let's just do it. Okay, so here's an exercise that I want you guys to try on your own. I'll post a solution somewhere later on, but yeah, just try this. Estimate what these would be. I haven't tried it on my own yet just because time. I literally just decided to do the stream in the morning, but yeah, so try that. I'll post a solution sometime soon. If you're watching this on Monday or later, then it's already posted in the description. Okay, now let's use Riemann sums to get something called integrals. So let's just do the integral from 0 to 1 of x squared dx. Basic integral, right? So that's going to be equal to limit as n approaches infinity of this thing. Actually, let's do 1 to 2. That way we have an a to work with. 1 plus... Okay, so what's delta x? That's 2 minus 1 divided by n, so 1 over n. K times 1 over n times delta x is 1 over n. Okay, so f of 1 plus k over n is going to be... If you plug that into the function, we get... first squared plus 2 times their product plus second squared, and we're multiplying that all by 1 over n, right? Okay, so multiply that all in, and I'm just gonna start simplifying this because I didn't leave enough space. Whoops, oh well. So we get 1 over n times the summation of basically 1 plus 2 over n squared times the summation of k plus 1 over n cubed times the summation of k squared. This is just n, because if you add 1 n times, you get n. So 1 over n times n equals 1, plus here, if you remember your things, it's going to be this. And then also the same thing. If you know your special sums, you'll get this fairly easily. Okay, so now you can see limit as n approaches infinity of 1 is just going to be 1. Whoops, that's going to be 2n squared. And then let me make sure I didn't mess anything up here either. That should be okay. Yeah, okay, so we're going to have 1 plus, and then here you're going to have 2 times n squared in the numerator, right? So, as n approaches infinity, you're essentially going to get 2 over 2, which is 1. And here, with those, you're going to end up with a 2n cubed in the numerator. So, if you take the limit to infinity, you're essentially going to get 2n cubed over 6n cubed, which is just 1/3. Add those together, and I believe you should get, let's see, I think 8/3? Correct me if I'm wrong.